And now tonight we are delighted to have our speaker, Eilon Adar, the director of the Zuckerberg Institute for Water Research and professor of hydrology at Gurion University. Professor Adar's main research activities relate to the quantitative assessment and accurate modeling of flow in complex groundwater systems in arid basins. He has developed the mixing cell model for groundwater flux, which uses data from environmental isotopic tracers together with hydrochemical parameters to generate accurate models of groundwater flux. Professor Adar earned bachelor's and master's degrees in geology, physical geography, and climatology from Hebrew University in Jerusalem, and a PhD in hydrology from the University of Arizona. Tonight, we are pleased to welcome him to learn more about his research into empirical and computational methods, and to learn more about the situation of hydrology in the Middle East. Professor Adar.
Thank you all for providing me with the opportunity to appear in front of you, and excuse me, please, for my voice. That what happened when you sent the desert man to the Arctic climate of Canada 2 days ago, minus 22, 25 centigrade. It was even tough for me. So I tried to recover this morning, and I hope it will work. This evening, well, I didn't know I'm allowed to speak here about my scientific achievements. So I promise you I will not dwell on any partial differential equation describing flow and transport in the unknown subsurface environment, although it's quite interesting. I rather will elaborate on one of the most important issues in the Middle East nowadays, aside of the politics, is the fact that one of the major resources, such as water, and I'm talking about fresh water, are diminishing. We all share a scarce resource, and during my presentation, I hope I shall be able to deliver the problematic issue about water utilization, water development, and how we manage to survive, and even beyond that, in such hostile, and I mean water-wise, environment. But I'm not just going to describe the problems, I'm going also to elaborate on solutions. These solutions came out of academic innovations, and they were nicely developed, and actually the results can be seen today. And I hope that this will leave you with the notion that in spite of the fact that we do lack a lot of water in order to survive, not just to develop ourselves, our society, and I mean our, I don't mean just Israel, I'm talking about Palestine, Egypt, Syria, Jordan, the entire Middle East. There is some hope, and I think we should be able to overcome the shortage in water by creating new water, affordable new water. So let's start. As you can see, I'm going to emphasize about the fact that water is indeed a scarce resource. And it is a vital resource that every nation, even the United States of America, is fighting to get its hand on. It's enough to mention the struggle about the Rio Bravo, Rio Grande water, and this is between the United States of America and the state of Mexico. Not mentioning the struggle between Texas and New Mexico, United States, about the little, how do you call it, Colorado aquifer, they call it. I don't know why it's Colorado in New Mexico, but they call it little Colorado aquifer. You know, between Mexico, State of Mexico and the United States, they negotiate, they talk. Between Texas and New Mexico, from my experience, first they shoot, then they talk. So, you know, I exaggerate a bit, but you understand, you know, the tension exists. So try to imagine that we have to share, in the Middle East, all countries share common resource, which is such important. And these are one of the few graphs I'm going to show. The problem became even more serious since we realized that the amount of water that is replenished the three major basins in the Middle East. I'm talking about Jordan, Palestine, and Israel, in this particular case, which we believe, which is about 1.5 billion cubic meters per year, and excuse me for using the metric system, but even in the University of Arizona in science, we use metric system. So, you know, from the year 1932, still under the British mandate, we established monitoring system, and this monitoring system allowed us to assess the amount of water that God provides us with every year. I'm talking about the amount of water that we can use, pump out, either from the aquifers or from the few rivers in the region. So in Israel and Palestine, we thought that we have, until I would say the mid-90s, we thought that we have about 1.5 billion cubic meters per year, but you see the fluctuations. And we do not have natural lakes to store the water from one year to another. The only fresh lake or reservoir in the Middle East, the entire Middle East, is the Sea of Galilee. That's it, in Israel. So, in good year, the water used to run to the sea, to the Mediterranean, or to the Dead Sea. And, you know, we could not actually transfer surplus from one year to another. But what you can see here, because we talk about climate change nowadays, we believe that we are expecting to have more and more dry years that we actually experienced already in the 60s, in the previous century, a series of 7, 8 dry years, recently in the late 90s, and also nowadays. The situation is very difficult, especially considering the fact that since the 60s, the population west of the Jordan River has been doubled. Okay? Not much water, or the same amount of water, with double population, with double amount of the people who are actually looking for water. So based on that, if I just take the water availability for Israel, here are the major basins. This is the Sea of Galilee basin, the Western Galilee aquifer, the coastal aquifer, the mountainous aquifer. All together, we believe that this is the amount we can pump out of each basin, summing up to about 1.5 billion cubic meters per year. However, based on the new assessment, we have much less. It is substantially much less, only 1.3 billion cubic meters, which is really significant. Nowadays, just 2.5 months ago, the National Water Authority came up with a new assessment based on new statistical assessment, and we actually think that we have 1.25 billion cubic meters per year to use. Bear in mind, we already produce more water than God provides us with. And no matter whether I'm a pessimist or optimist, the population west of the Jordan River will be doubled again, and this time in less than 18 years. So the rabbits can learn from us. So what shall we do? We shall have to double the amount of water available. And I'm not talking just about, you know, water in plastic bottles to drink for domestic consumption use. I'm talking about food. Especially nowadays with the crazy idea of growing, you know, biofuel in cultivated land. You know, we don't have enough food to feed the population, and here we are going to cut even food production to produce fuel, but this is another issue. Above all, not enough political struggle in the region. All major water resources in the region are transboundary. Cross-borders water resources. Even, the Jordan River, the only perennial stream that we used to have, and I emphasize used to have in the Middle East, in the Near East actually, Syria, Lebanon, Israel, Hashemite Kingdom of Jordan, Palestine, poor little river, 5 states fighting for the same water. But it's the same is true also for Turkey, the Euphrates and the Tigris, not mentioning the Nile, as we shall elaborate later on. So let's first see and look about the so-called surface basins. So we already mentioned the Upper Jordan Basin, Syria, Lebanon, Israel, Hashemite Kingdom of Jordan. The Dead Sea Basin, Jordan, Palestine, Israel. The coastal aquifer, Gaza, Palestine, Israel. The mountainous aquifer, West Bank, Palestine, Israel. Even the Negev Basin, the Eastern Nubian Central Aquifer, Sinai, Egypt, Israel. The DC Aquifer, Saudi Arabia, Jordan, and so on and so forth. Not enough complicated to look at the groundwater. The groundwater, the black arrows represent the flow, subsurface flow direction. So let's start. The mountain aquifer, you see it's flowing from the West Bank west, like all rivers flow to the sea. Also groundwater flow to the sea, flow west into Israel. Okay, next. Azraq Basin, we shall dwell on it later. Syria and Jordan. This used to be the backup water for the city of Amman. We shall see how depleted it is nowadays. The Nubian Sandstone Aquifer, Egypt, Sinai, Israel. Next, the coastal aquifer, Gaza, Palestine, Israel, and even the Negev or Arava aquifer, Hashemite Kingdom of Jordan, and Israel, and finally the DC aquifer. The most promising reservoir for Jordan, you will see Saudi Arabia and Jordan, and we shall see what happened to that. All are cross international borders. And we all probably aware of the fact that we are situated in the desert belts, the northern, which is the Sahara Desert, the Arabian Desert, the Gobi Desert in China, and the southern belt is the Atacama Desert in Chile, Peru, the Namibia Kalahari Desert in South Africa, and the Great Australian Desert, in Australia. So, in spite of the fact that we are talking about desert, as you can see here, surprisingly enough, the largest unexploited reservoirs, and I'm talking about groundwater reservoirs, were discovered underneath the Sahara and the Sub-Sahara Desert. These yellow clouds or spots represent more or less the size of the magnitude of this aquifer. This was discovered during what? Oil and gas exploration. They found gas, they found oil, but they found a lot of water. So you may ask yourself, if it is such a dry region, how come we do have water under the Sahara Desert, or how come we do have a lot of water under the Gobi Desert and the Kalahari Desert as well? Well, the reason that we have this water because this water was accumulated or had been accumulated during many, many generations, many, many years, and actually from the last ice age until today. So we are talking about old water. I don't want to use the word fossil because it's very common in the literature to read that this water is a fossil water, fossil aquifer. Well, I'm not aware of any fossil water in the universe. This is old water, but still it's part of the hydrologic system. Well, how much water do we have there? Not me. It is estimated by at least 150,000 cubic kilometers. Ladies and gentlemen, we are talking about the largest reservoir of water in the world, which is still waiting to be used. And I can tell you now, based on exploration that we did in China, the same is available under the Gobi Desert. Now in South Africa, we know that we have water under the Kalahari Desert. It is deep. It is maybe not as fresh as we used to have, but it is relatively fresh water. We call it brackish, we call it saline, or saline, depends on the pronunciation, but it means the same. It is one order of magnitude fresher than seawater. It is a great potential. And this is the proof. In the Western Sahara Desert, you find these lakes, oases of fresh water. These are two pictures. This is the Buzeima Lake in the Western Desert, and you can see these pictures taken from there. Or another one from Algeria, Jezero Lake. Look, this is not mirage, this is not miracle. It is a truth, it is true. And in the great dunes in the northeastern Gobi Desert in Inner Mongolia, we counted 104 lakes with fresh water similar to these ones. So it is a universal phenomenon. So let's see what Libya did about it. Look, now you see this light blue colored spots. This is more or less the magnitude of these subsurface groundwater reservoirs in the Central Sahara system in the Western Desert of Egypt. This is the DC Aquifer in Saudi Arabia. Those of you who can read, it says here, great man-made river. Maybe we have to change it to great man-made river. Because Gaddafi, no matter how crazy he was or he is, he did something logical. He said, we drilled hundreds of exploration boreholes for oil and gas. We found water. We miss water in Tripoli, Benghazi, and Tobruk. So why should we desalinate seawater with 35 grams of salts per liter while we can transfer water from the desert? And by the way, during the production of oil, you end up with a lot of water that you want to get rid of. So he pumped this water and desalinated water with 3.5 to 4 grams of salts per liter. So he's crazy, but not as crazy, regarding water at least. So this is the first, I would say, aqueduct that I'm aware of, taking water from the desert into the coastal plain, into the cultivated land. So this is the Libyan experience. And here you see, these are the pipelines from farms of production wells, and you see here, Egypt. Egypt did something else. Egypt relies entirely on the Nile. Here is the Nile, which is shared by 8, at least, countries, from the tropical zone of Rwanda, Burundi, Tanzania, Uganda, Kenya. This is the White Nile, which provides mainly, not only mainly, the large portion of floods during the early summertime, and the Blue Nile from the Ethiopia plateau. From this region, it crosses the desert of Sudan. Sudan is not utilizing much of this water, for reasons that I'm going to elaborate later on, and most of the water, well, not most, 90% or 87% actually of the water is used by the Egyptians. Historically, this was always like that, along the Nile. And as you can see here, all Egypt is concentrated along the Nile, the Kufa oasis, and along the delta. However, since the early 60s, something happened. What you see here, you see some spots, dark spots here. These are new cultivated fields based on additional water that they could pump from the artificial canal. This is an artificial canal from the Eastern Nile, excuse me, from the Eastern Nile wing. In addition, right here, a lot of water. now actually cultivate intensively all this basin, and the Western Desert. Along the highway from Cairo to Alexandria, you see many, many farms. Most of them rely on additional water from the Nile. Not solely on that, some nowadays based on also groundwater pumped from the sand dunes, but they prefer the Nile water because the Nile water is fresher. How come? Well, everything now is going through the so-called Aswan Dam. Already in the 40s, Aswan Dam, the little one, the small one, was elevated in order to create some kind of buffer, allowing the storage of floods in order to provide water to the delta. However, that was not enough. In the 60s, the former Soviet Union convinced Nasser that, with the Soviet know-how, they can turn Egypt into a huge oasis. And actually, they created the large Aswan Dam, which created Lake Nasser from southern Egypt up down to Sudan. Huge lake. The good thing about it, that actually it allowed 2, and in some cases even 3 crops per year versus 1 crop per year as traditionally experienced in the delta. However, the bad thing about it is that because this lake is located where? Almost in the hottest spot in the world, in the desert, they lose 11 billion cubic meters per year just by evaporation. And we all remember what evaporates, only H2O. All the dissolved minerals are left behind. So the chemical composition of the Nile water has been changed. Now these simple farmers, for them it's not trivial to accommodate with a new type of water. And this change was significant. It took a while to adjust to the new type of water. Syria. Well, in Syria, they rely on 2 rivers, the Euphrates. The Euphrates and the Tigris, mainly on the Euphrates. By the way, those who attended the lecture yesterday, remember, these stars represent already, points where water conflict was emerged. I don't say war, but water conflict. So you see a star here on the Euphrates between Turkey and Syria. Why is that? Because they constructed a dam here on the Euphrates. They call it Lake Assad. Here it is, right now here. And they started to irrigate the downstream river channel. Not much, or not that substantial as in Egypt. In Egypt they did much more. Why they could not do more? Because upstream here, this is the border between Syria and Turkey. What do we have here? Another reservoir, Ataturk. This reservoir is the largest Turkish reservoir, and actually they control the amount of water that they release to the Syrians. Now the Turks do not concern much about irrigation, they're concerned about hydropower, hydroelectric power. Another river which Syria uses is the Orontes. Now here again, the Euphrates fed up by the water or rainfall and snow from the Turkish plateau, Antalya plateau. The Orontes is actually fed by snow melt from the northern Lebanese mountains in Lebanon. So these 4 reservoirs actually depends on the amount of water that is released from Lebanon. Thanks God for the Syrians, they control Lebanon, and Lebanon cannot stop for the moment the flow of water into Syria. But bear in mind, the Orontes, before flowing into the Mediterranean, enters into Iskenderun, which is Turkey. So it's even more complicated, because Turkey wants its share as well, and the Syrian wanted to construct another dam over here, and the Turks said, forget it. You construct a dam here, we shall block the flow into Lake Assad right here. So it's a, give and take. Hashemite Kingdom of Jordan, even more complicated. Over there, they rely on groundwater, and we shall see the example from the DC aquifer and from the Azraq Basin, and on the Jordan water. Let's start. Start from the north. Here is the Sea of Galilee. This is the Golan Heights. This is Jabal al-Arab or Jabal Druz, the Druz Mountains. And the Azraq Basin used to be a huge oasis. I still remember it as a young student, traveling there, water flowing everywhere. They drilled hundreds of wells, 20 meters, 30 meters deep only, pumping water to Amman to back up the depleted groundwater wells, pumping groundwater to the growing city of Amman. And after less than 15 years, all this water has been depleted because they didn't calculate, they didn't assess how much water they have. They pumped, they abstracted by far more than God provided them. And actually nowadays, they rely on groundwater flow coming from Jabal Druz or Jabal al-Ahad into this basin. So Damascus right here, which is a very dry basin, is looking also for water. And they are looking to pump water from this huge reservoir. So try to imagine if they will start abstracting water from here, how they will affect the water flowing to Jordan. Further down, here is another Google Earth map. This is the Negev Desert of Israel. By the way, my campus is right here in the middle of nowhere. And people ask me, where are you coming from? I say, Google in end of the world / end of the world. You will get there. So this is the desert. Here is Sinai. This is Jordan, Saudi Arabia, the Gulf of Aqaba. Right here. This is the DC area, shared by Saudi Arabia and Jordan. Those who can see these green or dark spots here may ask themselves what these spots are. Pivot irrigation. The Saudis drilled hundreds and hundreds of deep wells. They can afford it. They can afford pumping and elevating deep groundwater to the surface. They have free energy, growing barley that they could buy in Canada, Argentina, or the United States for 10% of the price of the cost of growing. But they are proud that they can do that, and I think from their point of view, it is justified. However, it is the same basin, exactly the same basin, shared by Jordan and Saudi Arabia. Now, Jordan wanted to develop it and conduct an aqueduct, which they started to build in order to back up the water supply to the capital, Amman. It doesn't make sense anymore. Why? Look here. This is exactly this place. And I counted 97 wells in Jordan. Now you see many already fed up. That means dried up. This is one of the DC farms in 1985, and this is exactly the same farm in the year 2007. Why? Because the pumps were left above water table. And it's not because the Jordanians pumped the water. Their neighbors from the south pumped without actually coordinating the water abstraction with their neighbors. And remember, all major groundwater resources, as I already said, are cross-boundary or trans-boundary resources. Okay, so Jordan also relied on another source. And the other source is, and here you see the upper Jordan Basin. This is the Sea of Galilee. This is the Golan Heights, taken or occupied from Syria. This is the Yarmouk Basin. The Yarmouk Basin is 95% Syria and Jordan. Only very small section is flowing through Israel. Unlike the Jordan River, which I'm going to elaborate a little later, the Yarmouk River is about 20 to 25% perennial stream, and the rest floods. They don't have a buffering reservoir, lake, like we have along the Jordan River. They don't have any reservoir. So in order to be able to store from winter to summer, they constructed small dams, 2 small dams along the Yarmouk River. Why they do not construct a bigger one? Because on the Syrian side, Syria established 109 water tanks, water reservoirs, collecting runoff. So it doesn't make any sense. They collect most of the flood now, so very little is left now for Jordan. So Jordan tried to do the best. Here is the Yarmouk River. They diverted in this diversion, no big dam, they diverted through a tunnel. This is the tunnel into the Jordan Valley. This is the diversions. And here is the Yarmouk again with the diversion dam. And look, this is the Sea of Galilee. Here is the Yarmouk coming. This is the border between Israel and Jordan. And Jordan is very proud, and rightfully so, for turning the desert into really intensive productive land. They did a good job. And surplus of water, they even pump during the summertime to Amman, because Amman is drying up. They need more water. So, now to Israel. We described the situation around Israel. Now let's go to Israel. In Israel, as I said, we do have one fresh lake. This is, by the way, the Golan Heights, and this is the Yarmouk River, and this is Hashemite of Jordan. Come on, it's not the United States of America, it's not Canada. It's a very small region. Okay? So, it's a nice area, it's the center of recreation area in our country. Well, one lake. You know, we all compete for water. But, you know, even if God gives us something good, it's buried 212 meters below sea level. So even we wanted to use the water, and in the past we didn't want to use the water because the water was about 400 milligrams of chloride per liter, or about 900 milligrams of total dissolved solids, too salty to irrigate the oranges in Israel. And it is 212 meters below sea level, and in order to pump the water into the cultivated land of Israel, one had to pump it from minus 200 to plus 300, almost 520 meters. Well, at that time, it didn't pay. It didn't make economical sense at all. So, also Israel historically relied on groundwater. And here is the coastal planet for Israel. Every dot is a well, or an abstraction borehole, with different water quality. Now, red definitely represents lower quality. So, as you can see, most of the production wells nowadays produce water below the standard, so the water has to be treated or diluted in order to be used, because of high level of chlorine and relatively high level of nitrate. Also, by the way, this started to be developed, you know, more than 100 years ago. During the 30s, we discovered that actually we can penetrate the mountainous aquifer along the coastal aquifer. Now, the mountainous aquifer, which is replenished over the West Bank, and here you see the arrows of water flowing below, below surface, you realize that the northern basin flows into Israel. This is the green line. This is the border between Palestine and Israel. It flows into the Israel Valley, the Be'er Valley in Israel. And the western section flows into the Yarkon and Taninim, the two natural outlets of this aquifer. But Israel, in the 30s and 40s, even before the establishment of the state, started to drill hundreds of wells into this aquifer. Now, if you count the number of wells here in the coastal aquifer, the number of wells from the mountainous aquifer, now we understand why we are the Holy Land. So many borders. So, the Jordan River actually became a potential source only after the chief engineer of the TVA, Tennessee Valley Authority, Engineer Johnston, in 1957, paid a visit to Israel. And he got a mandate by both, of course, United States of America, Hussein, the late King Hussein of Jordan, and at that time, David Ben Gurion, our Prime Minister, to study the water potential in the entire Middle East and suggest how to allocate the water. And he came with an idea which was adopted by two countries, by Israel and Jordan. Jordan officially denied it because the Arab League didn't want to accept the recognition of the State of Israel. They said, we don't want to take part of it. Israel and Jordan unofficially, Israel officially decided that they are going to implement the water allocation. Now, what made the change? The Sea of Galilee is still 212 meters below sea level. Well, at that time, the population in Israel was dramatically increased. We decided that we have to secure our food production, and at that time we realized that water is a commodity. Water has a value. Water was nationalized like oil and gas. We are the first country in the world that gave water a real economical value. It is a commodity. And with this kind of attitude, they said, okay, we can invest, pump, and do something else. And this was done for the reason of security, which I'm going to elaborate later. So, first thing, in order to pump water from the Sea of Galilee, first of all, we had to improve its quality. And this was another reason why we decided that we can do that. Our hydrogeologists, my teachers, at the Hebrew University, and in the Tahal, the very famous engineering consulting company, they claim that they know where are the sources of salinity, of salty water that actually makes the Sea of Galilee brackish. And we drilled several boreholes into these deep reservoirs. The deepest one is 1,300 meters below surface. And we managed to pump the salty water, actually brines, and we created the diversion canal. And in less than 4 years, the water quality was improved from 400 or 450 milligrams of chlorine per liter to less than 200. Nowadays it's 165. Now it makes sense to pump the water. But beyond, so this is the national water carrier. By the way, here, before I continue, according to the peace treaty between Israel and Jordan, Israel is now allowing Jordan to pump excess or surplus of water from the Yarmouk River across only 5 miles into the Sea of Galilee. There is a meter, and in the summertime they are allowed to pump it back. It's their water. So it's the first time that the Sea of Galilee officially is now served as an operational reservoir for 2 countries. Unofficially also for the Palestinians. So the Sea of Galilee is now the operational reservoir. However, it's fed by water which comes from the upper Jordan River from 3 major springs which are fed by water which is replenished over Mount Hermon or Jabal Sheikh or in the Lebanese mountains. So here again, we do have water flowing from Israel, inside Israel, but one spring is in Lebanon, but most of the water, 98%, is actually recharged in a territory which is outside of Israel. And Damascus is only 30 miles away. And Damascus is a dry city. And they are looking for water. And if they start drilling into the same reservoir, definitely we see already a decrease in the discharge into the Jordan River. So here is the national water carrier, and I took this morning an effort to convert the units, and I hope I didn't make a mistake. So the maximum capacity is 350 million cubic meters per year, which is equivalent to 283 acre-foot per year water unit, equal to about 92,000 million gallons per year. Okay, fine. Or 620,000 cubic feet per year. It's a lot of water. Actually, during the last 10 years, we never meet this goal. We didn't have enough water. But the great thing about the national water carrier, unlike the Tennessee water system, that we actually established a spine, a net, across the entire country. This is, of course, for security. But beyond that, we can pump water from the sea, and we actually connected the same water distribution system to the groundwater system. So now we can control not just the quantity, but also the quality of the water. We can buffer between pumping water from the coastal aquifer, mountain aquifer, and the Sea of Galilee. This is the only country in the world that has such a system. Well, we are such a small country that we can afford having such a complex, advanced water distribution. And this actually allowed us, and here you can see from this satellite image, to push the desert further, and actually, again, Israel and Palestine are the only countries and entities that do not suffer from desertification. Actually, we, as you can see here from this satellite image, now we irrigate the North Lebanon desert and we turn it into a very productive land. However, everything depends on how much flow into the Sea of Galilee from the Golan Height and from the Jordan. And as I said, during the last dry years, series of dry years, this is the 8th years in a row where we get less than 70% of the average. And I'm not talking about 1.5 billion, I'm talking about 1.3 billion. So 70% of that. So this is how the Sea of Galilee looks like. And definitely, as you can see here, the amount of water that we used to produce from the Sea of Galilee from the 80s to until 2006 was about almost 400 million. And since then, it was declining and declining and declining. This is what probably we should pump out of the lake. And this is how the lake, this is the consequence. Now it's dropped to minus 214.3 meters below Mediterranean sea level. As a result, before Israel withdrew water from the Sea of Galilee, before Jordan took water from the Yarmouk, the Dead Sea used to get about 1.3 billion cubic meters per year. Since we and Jordan share the water exploitation, nowadays the Dead Sea gets about 50,000 acre-foot, 60 million cubic meters per year, and you can see how the Jordan River looks like near Jericho, about 10 kilometers, about 7 miles north of the Dead Sea. Also this year. And the consequence is very clear. We lost so many meters in about 50 years. And the Dead Sea, as you can see, and it's not funny, the Dead Sea is dying. Nowadays, during the last 5 years, we are losing 1.1 meter per year. Okay, with this pessimistic information, let's sum it up. Demand and actual consumption of water is far beyond the annual rate of replenishment. This is the statement. Water consumption, it means that water consumption is exceeding the safe yield. That means we pump, as I said, beyond what God actually provides us with. The annual renewable amount of water is about 1,400 cubic meters per person per year, which is less than 20% of the global average. And in spite of that, we are doing very well. How come? Well, water in the Middle East is a scarce resource, and I change it into scarce commodity. We gave it a value. And from now on, you will see what can be done. Okay, so what should we expect due to the natural and enhanced anthropogenic change in climate? I don't want to say climate change, but climate variations are definitely anticipated. Well, in a nutshell, definitely we should face aridization, drought, hunger, especially in those semi-arid zones and the desert countries, in which all population will suffer, definitely. Well, during the history of mankind, warm climate caused drying up of the semi-arid regions, especially along the global belt and along the sub-Sahel countries. This archaeological evidences support this statement very well. So, shall we despair? This I took from one of my students who, after he took his exam with me, and he was really, really in a bad mood. So I adapted it. Okay, what shall we do to secure water supply for future generations? What we have to do is implementing novel water innovations and technologies. And now I'm going to take two directions. One is adapting to the local water quality. That means, and maybe I failed to tell you, we don't actually miss water. We have plenty of water. Actually, this water is not in an appropriate quality or adequate quality for the end users. We are looking for fresh water. We have plenty of water in the sea. We have plenty of water in the groundwater. Unfortunately, it's brackish, saline, or salty water. So one way, whether or not we can adapt to this low quality of water, the other way is producing new water. We cannot avoid it. Remember what I said at the beginning. We already pump beyond what nature provides us with, and the population, and I'm an optimist, will be doubled west of the Jordan River in not 18 years, only 20 years. What shall we do? Okay, let's start with adaptation. An example from the Rift Valley between the Red Sea and the Dead Sea, and we are proud that we actually established artificial oases in the desert, not because it was a challenge, because we saw the economic potential. It's a great microclimate, and we turned ourselves to the major supplier of fresh vegetables to frozen Europe. Based on what? Based on local groundwater. So here we grow flowers, we grow excellent vegetables, high quality, and you see, even in the desert, you remember the lakes from the Sahara? Even in our desert, we do have groundwater, and this groundwater, unfortunately, it's brackish, saline. Where it comes from? It is seepage from the Nubian sandstone aquifer from Sinai, water coming from the Jordanian into the so-called Arava Valley shared by both Hashemite people of Jordan and Israel. The major source of replenishment nowadays are the winter floods. I don't know how many of you are familiar with winter floods in the desert. They last 10, 12, 14 hours, and that's it. And then they disappear. In order to not to lose the water into the Dead Sea, like around this village, this is Eliyahu, we constructed water dams. What these dams are for? Well, look, here is the Arava wash during flood, flowing this way. This is a side reservoir to collect some water. Look at the water, it's brownish. Why? It is 30% sediment, loaded with sediment. Now, when it's loaded with sediment, the rate of percolation is very slow because the sediment seals the top crust of the soil. So, like here, another reservoir was established to collect water, but not to store the water for the summertime. Why not to store the water? It is a desert. We evaporate. The evaporation rate is about 14 millimeters, half an inch per day. And remember, only H2O is evaporated. The salts and the sediments are left behind, deteriorating the rest of the water. So what is the purpose? The purpose is, here is again, to let the water stay for 2, 3, 4 days, let the sediment settle down, and when the water fresh enough and clear, as you can see here, now it's not as brownish as before, release the water for enhanced stream bed infiltration. Now, remember the reservoir that we saw next to the village? Here is the reservoir. This is a picture taken last year, full with water. After 4 days, the water has been released into the infiltration lagoons. This is, by the way, a 150,000 cubic meter covered reservoir excuse me, to store water and mix, water from brackish, fresh from the reservoir in order to create a melange of adequate quality of water. And here, the same infiltration lagoons under operation last year, and in a few weeks, we managed to elevate more than 30 feet the groundwater. It's a lot of water. It's a lot of water. Now, it's not only Israel, it's Israel and Jordan. So this reservoir is shared by both Israel and Jordan and managed together. So 6 reservoirs like this in order to enhance the water storage capacity. So this is one way. We enhance the input. Another way is to save and make the water utilization more efficient. So we moved into climate control cultivation system. The drip irrigation, very famous. So even in plastic houses or greenhouses, we cover the surface with plastic sheet, covering the drip irrigation system. Here we call it eggplants. Why we do it? In order to avoid, as you can see here, evaporation. To save on every drop of water. It is not just to save on water, because if this water would be evaporated, what would happen to the soil? Salt will be accumulated, because remember, only H2 evaporates and the salt is left behind. So this is one way. The second way is irrigation control. Sensors. We would like not to irrigate the sand or the soil or the root zone, but we would like to reach the stage where we irrigate the plant, only the plant. So only these sensors sense the moisture content in the root zone. Beyond that, in order to increase water use efficiency, we isolate the root zone in plastic sleeves. These are tomatoes.
Yeah.
So new approach that requires novel technologies. Everything is based on education, for sure, because simple farmer cannot accommodate such technology. So we are moving into pulse irrigation, which is controlled with potential and active transpiration. Let me elaborate on that. As a matter of fact, when these sensors read the appropriate soil moisture deficiency, the appropriate solar radiation which is now available for transpiration, and the soil air temperature, it calculates the rate of transpiration, and the computer, via the sensor, actually opens the subsurface drip irrigation. So actually we inject the water right when the plant needs the water. When I was a child, I do remember that in the news they used to convince farmers, don't be lazy, wake up and irrigate your land during nighttime to avoid evaporation. Well, it might be a good idea when you use sprinkling irrigation, but why to irrigate during nighttime when the plant do not transpire the water during nighttime? So now we inject the water only when the atmospheric micro conditions are right and appropriate to that the plant can actually utilize the water. We call it pulse irrigation. By this method, our farmers irrigate with 92% irrigation efficiency, the highest in the world with all the modesty. And now it's coming up like mushrooms. I mean, it's became very, very popular. Another way, and I have to rush, is to adapt the species to accommodate brackish water. And here you can see different grapes for wines. It turned out the desert climate is very good for the wine industry. And here we try to adapt the right species that shoots that can be grafted with commercial varieties. And here you can see Merlot producing excellent wine in the northern Negev, grafted on shoots that are resistant to water with 600 milligrams of chloride per liter. And it's sandy soil, so actually we can accommodate high salinity. And yes, we do have it's not a boutique wineries, I still call them garage wineries because they're so small, but it's coming up and gaining momentum. Not only grapes, but also vegetables. They are grafted, like tomatoes, peppers, and you will see they are grafted when they are 3 days old on salt-resistant shoots, and you see commercial peppers in the Negev desert, cherry tomatoes, and this species, different varieties, it is actually the small variation in salt content and microelements in the water supply, the applied water to the plant. And the European market takes it all. Melons. In the Negev desert, by the way, these are Gurion University melons. These species were developed in our university. They can tolerate up to 450, 500 milligram chlorine, ppm of chlorine. And you see, nice harvest, excellent taste. Unfortunately, they are not yellow in the outside, and this is a big problem in the market. Watermelon, mini watermelons, they are so heavy that they grow them in baskets. Very successful. Personal watermelon in the restaurant. In fact, from November to mid-March, frozen Europe, they buy it all. You cannot get it in the Israeli market. Well, what these are? Greenhouses. And they're green, but they do, in these greenhouses, we do not grow any vegetables. It turned out that since we pump this brackish water from about 1,000 meters below surface, it's warm water, 37 to 40 centigrades. We all know that the tropical oceans are deprived from the most commercial species. It turned also out that we know nowadays, and this is not our innovation, it's known everywhere, that you can take oceanic species, fish, and at the age of 17 to 21 days old, you can turn it in 24 hours from seawater quality to brackish water quality at a survival rate of about 70–75%, which is a lot. So, here we actually grow now, we have 15 fish farms in the Negev desert growing barramundi. Well, barramundi is not a very famous fish in the United States, but it's a very famous fish in Australia, and it is a delicacy in Japan and in Europe. Well, Israel is much closer to Europe than Australia. So now they grow the barramundi in these greenhouses, and remember, the fish do not drink water, they swim in the water. So actually you need very little amount of water. And remember, we pump it from about 1,000 meters, so you need energy. So we have to save on this water. The problem is that the fish contribute to the water ammonia. What we do with the water? And we want to circulate as much of water because we don't want to use much of antibiotics. So we want to release water, but we don't want to pump the water, to dump the water in the environment, into the environment, not to contaminate the aquifer and the soil. So we would like to evaporate the water. This is the best way to get rid of the water. To do so, you need evaporation lagoons, which are very expensive. So we found a very efficient machine that can take the water and evaporate it. This machine is right here behind. These are olive trees. But before we go to that, here we have some examples from fish and shrimp farms, not kosher shrimps, but shrimp farms in the Negev desert. Fish, very productive ones, and here the water from the fish farm irrigate olive plantations. Why? Or how come? How come olive tree can survive on brackish or saline water? Because the ammonia is converted into nitrate. You feed the fish with powder bones, which is rich with phosphate. You add some potassium that we take from the Dead Sea, and we compensate the poor trees that they get poor quality of water with surplus of nutrients. And they survive, not just survive, they produce excellent olive for oil. They're called Chalutza Negev oil. We used to import a lot of oil from Greece, Spain, and Italy. Because of dry years along the Mediterranean, nowadays, since we irrigate these trees, they do not suffer from dry years. We export olive oil to Italy and Spain. It's like selling ice to the Eskimos. I'm not kidding. You can buy, for me, I live in the desert. It's very difficult to get olive oil from there, from these plantations. You can buy it at the duty-free Ben Gurion airport in Tel Aviv. This is the best place to buy, that's where I get it. Ornamental fish farms in the Negev desert. We compete with the Japanese. And remember, Tel Aviv is much closer. It's only 4 hours time flight from Frankfurt, or 4.5 times hours flight from Paris, or 5 hours to London than from Tokyo, because Japan is the main producer of ornamental fish. They survive very well on brackish water. But also the same problem, what do we do with the water? So look, this farmer, by the way, he was one of our students, he created an evaporation lagoon? Not at all. It is lime. And what he grows here? Lily flowers. Lily flowers enjoy very much nitrate. They deplete the surplus of nitrate. He harvests the lily flowers and ship it together with the ornamental fish every week, cargo to Europe. And when the water reaches appropriate quality, he gives the water to his father, where he irrigates these palm trees with appropriate quality of water. So actually we have chain of users. User 1, fish farm, he grows lilies, flowers, and then he gives it to the third farm for growing these palm trees. Finally, vegetables, wines, fish. What about algae? What you see here, this is a new factory not too far from the city of Eilat in the Gulf. Well, in these tubes, actually what we grow, the Hematomus fluvialis, this algae which we harvest from the Pacific Ocean. And you see here at the seashore of Chile in the Atacama Desert, you see it's kind of pinky. By the way, only the salmon fish that migrate through this track along the Pacific Ocean during the right time and that they harvest this particular algae, they become really pinky. Most of the salmon is artificially colored with artificial pigment manufactured by a Swiss company at the cost of about $2,000 per pound. Okay? Well, and this is chemical, of course, it's not organic product. So, by the way, this algae is actually green most of the time. Only when it gets temperature shock, it becomes pink. We have brackish water, plenty. And solar energy, free of charge. Okay? So the next is to harvest it every 2.5 or 3 weeks. This is the paste. Dry it up and sell it in the market for double of the price you get for the synthetic pigment. And then you can feed the salmon farms with natural algae, so it's organic farming. And if you remember this fish, this is the salmon with this pigment. It's not a salmon. And this is the fish without this pigment. Actually, you see the fish are a bit pinky. This is the tilapia fish, the sandpaper fish from the Sea of Galilee, fed by the sandpit algae. And of course, they look like salmon, and they taste like sandpaper fish. And actually, you can play, with that. And this is a big hit in the market. So now, this is not enough. So we can adapt ourselves, and this is very important, to adapt to what we have. But this will not definitely not solve the problem. We have to come with new water. So we developed the technology for desalination of brackish water, groundwater. Developed the desalination technology for seawater, which is completely different. Now we are talking about reverse osmosis. Now you can see, we were not the first, actually the last ones. And here you see in Libya, along the Mediterranean, all these are desalination plants, but based on thermal desalination technology. Along the Red Sea, along the Gulf. Only Cyprus, only recently, 3 major stations where the biggest one in the world was inaugurated in Israel, the first one in the year 2005, and the last one this year. Why is that? Okay, these are the desalination plants. So actually, nowadays, at the cost of between 52 to 60 US cents per 256 gallons, American gallons, which is 1 cubic meter. Let's say 60 US cents per 1 cubic meter, we get the top quality of water from the sea, from the Mediterranean. How much we get? So you can see here, we started very modest. And this year, we shall be definitely, we are already here, 300 million cubic meters per year. This is the largest produced water in the world. All the water desalination in Libya or along the Gulf do not reach this capacity. We were waiting for the highest and the most efficient technology to be developed. I'm going to elaborate on this in a minute. On top of that, we started to desalinate also contaminated, partially saline groundwater. Not just because we need the water. It is more expensive than desalination of seawater. Why it is more expensive? Because they are smaller and we have to pump the water from groundwater. But we want to protect these production wells here, so we have to do that. So actually, we were waiting for the appropriate technology, which is embedded in this very thin layer, which is the RO, reverse osmosis membrane, polyamide membrane. It was invented more than 40 years ago. However, only 7 or 8 years ago, we reached the situation where we can actually maintain its performance for long time. We do have some membranes near Eilat, in the Gulf of Aqaba, which are performing top quality water more than 17 years now. So, if these membranes, which are very delicate, can last that long, and this is the most expensive part in the plant, we now can lower the price. Remember that pure water comes across this membrane, the brines are washed out, and we dump the brines back to the sea, and the most expensive part is the pressure, which means the energy. So, new water must be developed together with alternative, probably cheaper source of energy. One cannot be solved without the other. The cheapest cost that we achieved so far is 3.75 kilowatt hour per 1 cubic meter, which is really not much. When you take your SUV to the supermarket, you actually, with this gas, if you drive only back and forth 10 miles, you can produce about 25 cubic meters of water with this energy. So it's a lot. That means the energy component is not that high. However, it is important because so far we use crude oil. So we are looking for alternative sources. This is 400 square yards solar dish that concentrate energy, and we are looking for solar and a solar desalination system. Some two crazy ideas. This is wind-driven desalination system. Instead of producing electricity, let's produce pressure. So the wings will operate a pump, and the pump will pressurize the water. Series of windmills like this, they pump instead of creating electricity and convert the electricity into pressure, use it directly to pump the water into the cassettes, the reverse osmosis cassettes. I can show it because we issued patent on that, okay? And we work very hard to look for alternative energy because crude oil, every cubic meter, we contribute to the CO2 emission, and of course we want to avoid it. And finally, what we do about this inland desalination. Remember that we get permeate, which is the fresh water, and we also get the concentrates. What do we do with the concentrates? If we are far away from the ocean, far away from the sea, where we are going to dump it? So we try to reach the stage where we can get crystals, because crystals we can bury. We can easily accommodate salt as it forms its crystals rather than as saline brines. The government of Australia do not let any company construct inland desalination plant unless they can show that they can produce fresh water and solid crystals of salts. And as you can see here, we developed a prototype, and now here it's covered already with salt. This is a nice wind-driven brine device to get salt crystals. So, no, we are not dealing with gold. But water is as important as gold, and water needs care, but water needs really care and attention. And if not, if we don't adapt the so-called holistic integrated approach to avoid environmental catastrophe, even we go with the most advanced technology, I'm afraid we should reach an environmental disaster. And I don't want to mention Aral Sea, I don't want to mention the Dead Sea, which is dying. I mean, we work very hard to produce new water, but we have to take the holistic approach, the holistic environmental approach, to look left and right and make sure that we make as little damage as possible on the environment. Thank you very much.
And now we will take some questions. Since it is a little hard to hear in this room, if you would stand when you're asking your question and please speak up.
Yes, sir.
You mentioned earlier in the talk that the Nile went through the Sudan, but they don't use the water. You didn't elaborate on that at this point.
Well, Sudan used very little of the water, and Sudan wanted to use much more. And as a matter of fact, in 1984, Sudan actually challenged Egypt. And they said, okay, you guys claim that you have the so-called Mediterranean, the downstream rights, because for thousands of years you used the water of the Nile, which is true. And Egypt said to Sudan, you have all the rights to do so. However, you there taking 1 cubic meters from what coming to Egypt. So it means take. No. Because what Egypt said, and that was true, and let me get to the slide, and this was really correct, is you the Sudanese, have the option to get water from the Nile without interrupting the downstream flow. How come? Okay. Right here, along the White Nile, after it gets out from the down from Uganda, the water flows through the so-called Sud marshy area before it gets into Khartoum. The Sud marshy area during the flood time, during the monsoon season, actually it's flooded up. We are talking about at least 167 to 180,000 square kilometers, from which 21 to 23 billion cubic meters are lost by evaporation. What Egypt said, the engineers, you dig a canal across the marshy area, let the water flow directly, and you have 21 billion. And they started to do so. Unfortunately, 2 years after, huge flood along the Nile destroyed all the canals, all the machinery, reminding me a bit about the Colorado and Lake Salton, the Salton Lake in California in the earlier previous century. So everything, Sudan didn't give up. At that time, Anwar Sadat sent 4 MiGs just to fly above Khartoum, and that was enough. They stopped with water obstruction from the Nile. Yes?
Okay, you mentioned these 2 options. One, use what you've gotten, use the low quality water and make more fresh water.
And make?
More fresh water, basically.
Oh, yeah, okay. Go.
Okay. What about the third option about decreasing the growth of population? That's a third option. I know there are social things against it, but I'm thinking, in 20 years you're saying the population in the whole area doubles, and then I'm thinking, and we'll be able to handle it maybe. Then the next 20 years, powers of 2, they grow up rapidly.
Do you have any idea how to do that?
That I'm asking you to expand on it.
Well, I think I have quite a lot of knowledge, but it's limited. No, seriously.
I'll say it doesn't seem possible.
No. Now seriously. The increase in population, 90% will not be on the Israeli side. It will be among the Palestinians.
Yeah.
And it's projected. Well, I cannot foresee that in the next generation we shall be able to lower the rate of the growing rate of population. Maybe, when education will be leveraged, I'm sure that we should see, a decrease.
But you're saying it is 90%
But
among the Jordanians? Okay.
No, Palestinians and Jordanians. But it's not a big deal. Come on. We need 100 million cubic of meter per year. It is $50 million. It's nothing. If our economy can accommodate it, I'm talking about nationwide, it's not our private money. It's nothing. I do remember late Prime Minister Rabin said that when we reached a dispute with Jordan about 30 million cubic meters near the city of Eilat in Aqaba, and he approached us, the hydrology, saying, you say that you can desalinate in 5 years water at the cost of, at that time we thought, 75 cents. He said, for that, we are going to struggle? Let's pay for it. So, look, it's now feasible. It's something that can be achieved. And it is even economically justified. Look, with all modesty, when we inaugurated the national water carrier, we started to pump water from the Sea of Galilee in 1964, let's say 1965. At that time, the agricultural sector of Israel consumed 1.1 billion cubic meters per year. 100% fresh water. At that time, our population was 3.5 million. Nowadays, 45 years later, the agricultural sector consumes 1 million. Almost the same. For all practical purposes, it's the same amount of water, out of which 78% is reclaimed sewage water. And the agricultural production is now exactly 9.89 times higher, 10 times higher, 1 order of magnitude higher. And the population now is 7 million. With the same amount of water, total, out of which only 25% roughly is fresh water. In 2 years' time, it will end with about, and stabilize, 20% fresh water. Actually, the agricultural sector is actually a link in the process of treating the water, because we have to treat the water. We are not allowed to dump it into the Mediterranean. We signed the Barcelona Treaty. So Israel now treats and consumes almost 80% of the sewage. Actually, I'm sorry, no, it's a mistake. 68% of our sewage. Next to us in the world is Spain, with 22%. In 2 years or 3 years' time, we shall reach 75% of the sewage treated and reused. Of course, in subsurface drip irrigation system and in surface drip irrigation systems in plantations. And we sell the product with no problems into the EP European market with all the EP approvals. Yes, sir.
Yeah, no. I have 2 questions. One was, give me the right frame. What is the Galilee at 400 and then you took it down to 200 parts per something, say
Sea of Galilee?
the Sea of Galilee.
Yes, 400 about, yeah. Now, before.
What's good potable water?
Okay.
I have no frame of
It's an excellent question. Well, it depends. Would I be a citrus tree, okay, if you provide me with water which contains above 250 milligrams of chlorine per liter, I would collapse.
How about from the person?
People can drink even beyond that. However, our kidney, can accommodate it. However, the taste is not that good. Now, seriously, we drink water without any problems, and actually we enjoy water with about from 20 to 80 milligrams chlorine per liter without any problems, and it's tasty. You know that we take the desalinated water and we pass it through gravels of chalk and gravels of chalk and forgot the other name of the, in order to elevate a bit the salinity of getting calcium and magnesium, chalk and dolomite, I'm sorry, chalk and dolomite, to get some calcium and magnesium into the water to increase the leverage the taste.
And the second question
Yeah.
is quickly, if you dumped a bundle of dye in water at one point in an aquifer, how when would you see it 20 miles, 30 kilometers downstream?
Well, it depends. If you're in former Yugoslavia, Slovenia, where you have the karst system, you know, subsurface rivers, it's a matter of days, hours. In the Middle East, everything is going slow. I'm talking about 1 meter per year. That's it. Naturally. However, if you start pumping, you don't pump nothing. So you enhance your truck for water.
You're increasing the gradient.
Absolutely. You increase the gradient, the driving force. Here you get into my differential equations. So then it's much faster.
It's good. I have a question. My name is Richard Dawson from George Mason University. And what was you think that water is being used as a geopolitical weapon in the Middle East? Have you studied that part of the problem, of the issue? Like gas is being used as a geopolitical weapon, for example, in the Andean region or in Europe.
You use the word weapon, which I don't like, and it's not because I'm...
It's as an analogy.
Okay.
Just an analogy.
Let me tell you one thing. I answer you with a statement,
Okay.
and I take it seriously. After the failure of the Oslo Accord, the only active commission among the Palestinians and the Israelis is the Water Commission. We meet twice a month in Ramallah, Jerusalem, and Tel Aviv. And there is a formal declaration. Water is kept out of conflict. And in spite of what's going on in Gaza, and the day before yesterday launched a Grad rocket into my campus in Beersheba. Every day we pump 3,000 cubic meters of fresh water from the desalination plant to Gaza City. You know why? Because it's not healthy to have a thirsty neighbor. And water is kept out of conflict. The pipelines to the settlements in the West Bank are on surface. You know why they are not damaged? Because the same pipeline feeds Palestinian Israeli villages.
So there's no conflict?
I don't want to say that. There is conflict. There is conflict. But I can tell you, I know my colleagues from the Palestinian Water Authority. I know the Palestinian Water Minister. They have a minister for water. We have a Water Authority director. They have a minister. And it's justified. We actually agree on the solution. The dispute is that the Palestinian wants to sign an agreement and implement it on water right now. The Israeli attitude is that we are willing to sign as part of the global peace treaty, like the Egyptian model, like the Jordanian model. It's not a secret. We actually signed a practical treaty with Jordan about water 15 years before the formal peace treaty. But we were waiting for the formal, global, holistic treaty to be signed because water is important in our side. So, is it a weapon? Take it from here. Yes, no. Okay? So, yes, it is a very strategic source that everyone is watching very carefully.
Thank you.
Couple more questions?
What are the practical conservation in the use of water and drinking water, showering, swimming pools, things like that? How do you use water for people use like that?
The same you use, but we might use much less. And you know why? Because we pay fortune for that. This is the way. To produce the water at the gate of the plant, as I said, it's about 60 US cents. The water distribution from the plant, you know, it's like groundwater, it's the same. It's about additional $50. You know how much we pay for the water? We pay $2 per cubic meter, at least. Why? Because the water has a value. Would I own a private well? I do not, even not in my village. And I should get a permit to pump a certain quota. I pay for the energy, and I pay for the water that I take from the National Water Reserve. It has a value. Actually, in the cities, in some places, some communities, they pay up to $4 per cubic meter because you pay for the water and you pay for the treatment. So nowadays there is a big debate in Israel that it's too much and it's too tough on the lower class, and they want to ease it a bit. But that's how we manage so far to save on water, to convince my kids, you know, to sing but not in the shower.
You know why I asked the question is, I would think there would be the development of some type of technology. Just for example, when you go to the sink or when you go to a shower, there's lots of periods of time during which you're either brushing your teeth or taking a shower that you don't need the water. And it's beyond my belief, it's beyond me to understand why we don't have some type of a foot pedal or something that can regulate the water to be on when we actually use it, as opposed to the period when
Hey,
it's...
you have a child.
What?
You have now a child. Go for it. But I tell you something, that in our home, in my home, there is first of all, we have a solar heater, definitely. It's mandatory in every house in Israel. Apartment or house, you have to have a solar heater. But we do have, even aside of the central heating system, we do have now a small device that turns the electricity and heats the water from the first cup. So you don't have to wait even, the 2 minutes for the hot water to reach the tank, just to save on water. But you know what? Between you and me, it's cheaper to desalinate 10,000 more million cubic meters than to go for all these stores. It's important, to educate the people. But from economical point of view, and I'm not an economist, but I listen to my colleagues, they say, okay, you keep, preaching, it's important, to educate the public, but we should produce more water and we stop the problem.
One last short question. We have one back here.
Yeah, I always have a question when I see presentations like this that show sort of an array of the applications of water-conserving technologies, because...
I can turn it down.
What's that? Because I feel like so often they turn into just isolated case studies, and I'm wondering how...
Is it isolated? I was talking about the entire Middle East.
Well, I mean, I'm wondering how, you're showing the drip irrigation applications, the reuse of water through several stages, and I'm wondering how extensive that is in the agricultural sector in Israel.
Excellent. Well, how do you think we managed in 45 years to increase the production by 1 order of magnitude without increasing the amount of water supply? Water use efficiency. It is implemented, but not just in Israel. In Palestine, in Egypt, in Jordan, it has been adopted. In China, in India, not in the United States. Only a bit in California. You know why? Because you don't pay for the water. You pay more for the air than for the water. I'm kidding, of course. I mean, water here is free. It has a value, but you do not appreciate its value. So there is no incentive to save on water here. Yes, it's implemented. This is on a daily basis. But, and this I would like to finish here because I lost my voice completely. Everything depends on education, and I'm not talking about higher education. When you mention farmer in Europe, and even in the United States of America, you're talking about low class or lower class.